Okay, so now you know what a convolution is, and we can start building our convolutional neural network. So here we go back to our example of the C410 dataset. We have the input layer with 3 channels, red, green, blue, of 32 by 32 pixel images. Then I remember earlier what we did is just flatten the image. Now we are not doing this until the very end. Rather, we are applying these filters. So what we have is a convolution layer. And we define that we want to have 10 different filters in the first layer. Each filter has a size of 4 by 4 times 3 because there are these 3 different channels. And we define that we want a stride of 2 and padding the same, meaning just like I showed you here, we are padding around with 0 so that the output is the same size as the input. So what we get is, because we have 10 filters, we now have 10 channels on the output side. And because we use the stride of 2, we effectively halved the size of the image from 32 by 32 to 16 by 16. Then we have another convolution layer, and here we say we want to have 20 filters. And we make it smaller still, 3 by 3, and use a stride of 2. So it will halve again the size of the image. And then at the end, we apply a flatten layer. So we make this into a vector here. We get 1,280 nodes. And like before, the output layer has 10 nodes because we have the 10 classes for giving us the example, the result, the output of the network. So again, how do we define this in Keras? Well, input layer is the same as before, but now we have 2 layers for 2D convolutions. And just like we defined in the image here, the first layer has 10 filters of size by 4 by 4, strides 2, padding the same. And then the next filter coming afterwards has 20 filters, 3 by 3, 2 strides, and again, same padding. And you can always see how the layers are chained one after the other. So when you build this kind of network, at the moment we have only 2 layers, but they can become quite a bit bigger. It's important that you keep track of what exactly you have at input and output for each layer so that you can define the right size of the next layer. So you have to be able to understand and analyze the network architecture. So the input size is 32 by 32 times 3. This is what we established before. And in Keras, there is another parameter here, which we set to none, which corresponds to the question mark here. This just tells Keras that we can process the inputs in batch as many images as it wants. So it would be different if we had some, for example, some time series data where you can process the next one only after processing the previous one. Now we go through the first convolution layer. Remember, we have filters of size 4 by 4 times the 3 color channels. So the kernel size is 4 by 4. So how many weights do we have here? We have, I have to connect this for each filter. So 10 filters times 4 times 4 times 3 plus 1. Where's the plus 1 coming from? I hope you remember. So if you calculate this, we have 490 weights to calculate here. The depth of a filter in a layer is always equal to the number of channels in the preceding layer. Yeah, otherwise the whole network wouldn't connect. Yeah, it wouldn't compile, it would just fall apart. So here you can see in the second convolution layer, we have 10 channels because this is what we got from the previous layer. So here we have 10 channels as output, and this is what has to come into the next channel here. So with this, there is a handy formula that you can use to calculate the output shape for each convolution layer, and it's the one given here. So none is just, again, this wildcard here. And then for the dimension, we have input height and width divided by stride and the number of filters. So if you apply this formula to the network here, you end up after the input channel with 16 by 16 by 10. So then the second convolution layer, 20 filters of size 3 by 3, depth 10. And we'll do this in a minute as an exercise. Then finally, at the end, we have the flatten operation. So we are transforming the 8 by 8 times 20, which gives us a vector of 1,280 units. Again, using the flatten that before we had directly on the input layer. And then output, just like before, 10 units fully connected, dense layer using softmax activation. So just to make sure you get through this network architecture and understand what's going on with input and output, try out this second task on the worksheet, and I'll see you back soon.